Alright, good afternoon folks. I'll get started. So this is week 4 and I want to finish up on the manufacturing and the module assembly of the silicon based solar cells, and then we'll start this new topic of light trapping, and I've kept around 15-20 minutes for discussing the problem set too, so hopefully you had a chance to take a look at that. So before I get started, I came across this energy week which is happening at Stanford this week. There are quite a few interesting lectures. There's a talk by Al Gore tomorrow in Memorial Auditorium. There's a lecture by Stephen Chu, who used to be the Secretary of Energy, on Wednesday. There's also this panel by Solar Impulse, which is an aircraft which flies on using solar electricity, and all of these are scheduled this week, so I encourage you to take a look. All of them are free to attend, and the website for this is energyweek.stanford.edu. So go take a look, and if you have time, I encourage you to attend some of these events. So picking up from where we left in the class on Wednesday, so I described these, we had made these individual solar cells, and these had this p-type contacts on the top and this n-type contact on the bottom. So now when I assemble them in a module, I need to somehow connect these diodes in series with each other. So the way I do that is I take these this is called as usually the bus bar. So this is called the bus bar for each of the solar cells, and it has many of these fingers, and each of them are collecting the carriers which are generated. And you can see that this bus bar has this triangular shape because as you move along this bus bar, you're collecting more and more current. So your I, as you're moving along this direction, is increasing. So to minimize that resistive loss, or that I square R loss, as you move along this length of the solar cell, usually increase the width of this bus bar. And then at the end of this bus bar, you have these ribbons coming out, and you take those ribbons and take that ribbon and connect it to the bottom of the other cell, and that's how you connect them in series. And when you can either connect these cells in series, or you could connect them in parallel. And actually, you guys can pull up a table over here. You want to pull up a table here? Okay. So you could either connect them in parallel, or you could connect them in series. And one of the students pointed me out that why do you need, usually you have 2 of these bus bars on each of the cells. So why do you need 2? Why can't you just have 1? Because if you have 2, you have more shading, more of these, more of the top area occupied by the bus bar. So why not just have 1? Yes. Sorry, can you repeat that? So one thing is that if you have too much current, you typically, if you have a narrow bus bar, then you'll have a lot of I square R loss. So, but I could make a wider bus bar instead of making 2, right, to minimize that same resistive loss. So it's more of a practical reason, and that's something you'll realize when you do your project where you solder these individual cells. It's designed from a point of redundancy, that what if one of these connection gets open, or while assembling them, what if you don't connect one properly. So to ensure that to build some redundancy into the system, that's another reason why you typically have 2 of these bus bar per cell. So now if you connect them in parallel, then what will happen is that your open circuit voltage, which is defined by each of the cell, that will remain the same, while your current or your short circuit current, that will increase depending upon how many of these you connect in parallel. On the other hand, if you connect them in series, then essentially the current which is flowing through these cells remains the constant, because that same current which is flowing across these cells. So the current remains the constant, but the voltage or the open circuit voltage, it gets amplified depending upon how many of these cells you are connecting in series. So usually these modules, they use a combination of both series and parallel connections. And this is a finished up module. So typically you have around 36 or 72 of these cells connected in series. The reason for that is that if you have 36 of these cells, and assuming maximum power voltage of approximately 0.5 volts. So usually you have open circuit voltage which is around 0.6, 0.7 volt for a silicon cell. The point at which this maximum power occurs is approximately 0.5 volt. So if that is the case and 36 of them are in series, then the voltage that I'll get across this panel is approximately 18 volt. Similarly, if I have 72 of them, then the voltage that I'll get is approximately 36 volt. And this is typically useful. This voltage levels are useful, especially when you are using these panels directly to charge up a battery. So a lot of the batteries, they operate at 12 volt or they operate at 18 volt, and it's recommended that when you are charging these batteries, you charge it with a voltage which is 1.5 times of that. So you achieve that by connecting these 36 cells in series, or connecting these 72 cells in series. So once you have done this connection, the next thing to do is to laminate this or encapsulate these panels. So that is done next. So the way this is done is typically you have these cells, you lay them out on this back sheet, which is made up of typically a reflecting material, and that is meant so that your diffusive components which are shining on this sheet can hopefully still be part of it, can still be captured by this module. And then this is covered by this sheet of glass, and this is embedded in this polymer material, and then you take this and give it some thermal budget, and that essentially sticks this together, and then your module is ready to go. And one of the problems that one can find oneself in if you connect a lot of these cells in series is that what if one of these cells, essentially one of these connection breaks, or there's an open circuit condition here. Or the other thing which can happen is that, for example, this panel is on a rooftop. What if a leaf falls in and it covers one of these cells completely? Or there's some soiling effect or something such that one of these cells essentially is covered, and now it's no longer conducting current. So if a lot of them aren't connected in series, it will essentially you'll have no current flowing throughout the whole panel, or your voltage across this whole panel will shoot up quite a lot. So to avoid that, the technique that is used is you connect a bypass diode. So if you have let's say in this case 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 of you have 36 cells over here. So these are connected in series like this. So after every 18 cells, you connect a bypass diode over here. So if the voltage across this cell shoots up very high, or there's some problem in this part of the panel, this bypass diode would take over, and essentially if the voltage across these 36 cells is higher, or one of them is disconnected, the current can now flow through this bypass diode. So this technique is also used whenever, especially if you have a large number of these cells in series. So you often find bypass diodes, and they are connected on one side of the panel, and they allow for this parallel path, which becomes available if something goes wrong in the cells in this series. So let me give you, where the industry is kind of today. So we have on one end of the spectrum, we have what is called as these Gen 2 cells, which is the back contact cell, and the company which is most famous for pioneering that is SunPower. But most of the market, more than 80 or 90% of the shipments are based on that passivated emitter design, where you have aluminum alloying from the back and a silver contact from the top. So it's both front and back contacts, both contacts at the front of the solar cell as well as contact at the bottom of the solar cell. And basically the path for everybody is clear. Everybody wants to move from this to this. The whole industry wants to move from this Gen 1 to this all back contacted design. But the margins in this business are so low, and that happens especially that when things become commoditized, these cells are sold in a commodity market. So the incentive or the capacity or the appetite of making those investments to go from here to here is quite low. So what people are thinking, that instead they'll go in baby steps. So they'll take baby steps and they'll add one thing at a time to reach to this Gen 2 stage, and each will give them some boost in the efficiencies. So some of the things which are the industry is currently planning is what is, I'll explain, called as the double printing, the selective emitter, similarly passivating both sides. Currently only the front side is passivated with the silicon oxide, silicon nitride, but they want to passivate the back side as well. So let me explain some of these baby steps that the industry is currently planning. So if we have to have a front contact, we could essentially have it laid out like this, where it's more horizontal in nature. But the trade-off in that case is that it gives you a lot of shading. So 7% of your area, your top area, is occupied by these contacts. You could make this same contact more vertical, and both would have the same cross-sectional area, so they'll have the same resistance, or they'll have the same I-squared loss. But the problem in this case is that while this scheme, which is laid out horizontal, it gives you shading when the light is shining directly from the top, versus this scheme gives you more shading when the light is coming from the side. So this might be a good design when the light is coming directly from the top, but over the course of the day, if your sun is shining at an angle, this might in fact end up giving more shading. Another thing is, with the manufacturing of this more vertical kind of printed fingers, is that your mask needs to be more finely designed. It needs to be replaced more often, and so on. So there are other manufacturing issues with that. So what the industry is currently planning is to move to this scheme which is called as double print, where instead of printing this finger in one shot, you print essentially one thing which is more horizontal and more wider, and then you come back, but again you're not using lithography, neither are you using any alignment mark, but you come back and you align this very precisely, and all this alignment is done in that screen printing equipment itself, and then you come back and print something which is more vertical. So instead of printing once, you print twice, and this gives you a small, again a baby step increase in the efficiency as well. And it uses a less amount of paste as well, because instead of making this whole thing like a rectangle, now you're replacing it by these two of these prints which occupy less volume. So this is some manufacturers have already started implementing it, but this is something that is going to happen. Next thing which is in the works again is to use a selective emitter design. So I explained to you that whatever is generated in this heavily doped region is collected with a very low efficiency. Also, increasing the doping over here, it increases your carrier recombination in that region. So what you ideally want is you want a very shallow emitter, and you want it lightly doped as well. But where you are making the contact, at that point you want a heavy doping. So you will essentially want an N doping here and N++ doping here, instead of having this uniformly high doping throughout your emitter. So this is what I described in the last class as well. This is called as a selective emitter design. And again, this is something that is being considered by the industry as well. So this is where most of these Gen 1 systems stand. So they are connected like this, where you have this bus bar and it needs to connect the top of one cell to the bottom of this other cell. And just making that, as you'll realize when you do your project, is something where you can easily break a module, or you could have not proper connections. While these back contacted design, they are essentially they have both of their contacts at the back, so they are very easy to assemble in a module. You assemble them just like you assemble your PCBs. You just surface mount them. So you take these cells and just place them on something on which you have a circuit board or equivalent of that, on which you have these things already printed. And so these things are more easier to mount and make a module. So again, this is the current timeline, and there could be multiple schemes of making these back contacts. So the one which is used by SunPower is called the interdigitated back contact, where you have these fingers of these two contacts which are interdigitated with each other. And but there could be other schemes such as emitter wrap through and metal wrap through, and these are described in more detail on the videos which are on the class website. So this is a squish chart of where the cost lies. So you have different steps in your process, starting all the way from polysilicon to making an ingot out of it, cutting into wafer, then making a cell, then making a module, and then finally the system cost. So if you think of just these steps, starting from the polysilicon and going all the way to the wafers, and you squish the cost associated with that, so you'll see that around 25% of the total system cost is located just in the wafers, just starting from that polysilicon and making a wafer out of it. So this got a lot of people interested back in 2007, 2008 time frame, especially when the polysilicon prices were still high. And people are trying different approaches to essentially still get a high quality crystal, but get it at a lower price. So this is a good time to put a plug for our next speaker, who's representing this startup company SelectCell, which has a unique approach to making this thin films of crystalline silicon. Again, they're not the only people in this game. There are other companies. There's one company called 1366. Alta Devices had its own scheme of doing this with gallium arsenide. So there's a lot of effort focused on reducing this cost associated with making the wafer. The cell, if you look at all the steps that I described to you in the last class, all that firing, printing aluminum, printing silver, the total cost for that is only 15% of the total module cost. Making the module, in fact, it involves a lot of labor. It's a labor-intensive process, and it can add up to 23% to the cost as well. So if you can come up with easier ways which allow you to make this module at a lower cost, you can get a much, you can reduce the overall cost by 23%. So any questions on this? So this is just the ranking of the different crystalline silicon players, and you see a lot of Asian names over here. So in fact, 4 out of the top Three out of the top four players, Yingli, Suntech, and Trina. Yingli, in fact, sponsored. They were a sponsor for I think the Beijing Olympics, and not the Beijing Olympics. Which was the last Olympics? Beijing Olympics. The last Olympics, and they were the only Chinese company who was a sponsor of that. So, First Solar is an American company. It's a cadmium telluride based cell, which we'll talk about later when we talk about thin film technology. SunPower, which has in fact the highest efficiency cell, does fare. They do come in the top 10, but they are not, as higher as we would expect them to be. Okay. So what I do at that end of every module, I give some resources for you to go and look at. So for reading about how these cells and these modules are assembled, a good resource is this Handbook of Photovoltaics book, and it's a new book, and that's the reason it came out last 2 years back, and it's again available for free for all Stanford students. And the other prescribed book that I have for this class, you can also read some chapters from that. And there's a handout which gives if you're a history buff like me and you want to look at historical evolution of things, then that is a good resource in that. Any questions on cell, on module and stuff?